Okay, BYP here, your RF redneck, experimenting with dipoles. Why? Why is it that the feed point resistive value is controlled by the height of the feed point and not the rest of the wire? Terman says so in the Radio Engineer's Handbook, and I have verification of that. The purpose for building the quarter wave end fed was not to build an end fed. That's a waste of time. That was done to get half of a dipole with no transmission line perpendicular to ground. The feed line is in line along the cord that holds the end of the wire. And the unfed did not care a bit whether it was raised or lowered. So the resistive value is not controlled by the height. But why is it in a dipole? I noticed, according to this fantastic picture, that when I picked up the end of the 20-meter dipole line at the ground and lifted it, went back 50 feet and lifted it, nothing happened. But when I tilted the line side to side along the wire, significant change in match. And this revolves around the question of exactly what happens at that feed point. Imagine that energy has just reached the end of that tubular line where the circle is, and is being coupled out on those two wires, that braid twisted up and that center conductor soldered to the wires. The charge energy has to continue on the wires, that's obvious. But it's not so obvious how the field energy also comes out and ends up a short distance away from each wire, being coupled to the ground. Well, I did an experiment months ago. 2 pieces of number 6 wire, tied end to end and suspended from the ceiling. And there they lay back there. And here's today's experiment. A couple foot of number 6 tied off to the ceiling so a crap load of charge can come down from the ceiling, and a piece going down towards the floor. And directly I referenced that to the wall over there. And the skinny mini blue wires went to the high dollar capacitance meter. And 4 foot of cheap RG58 coax. Coax cable tends to have about 30 picofarad per foot. So about 120 puff worth of capacitance there. But when I tested just about a 1/4 inch spacing between two number 6 wires, I couldn't measure the capacitance. Could not measure it. It was more indicating charge from the ceiling than anything else. I calculated that between 2 number 6 wires, 0.2 inch in diameter, it calculates to 0.03 picofarad. That is precious little capacitance between the wires to couple anything, but it doesn't take much. What I found evidence of and tested today was that the reason that the match is sensitive to the transmission line going sideways along the wires is that when those charges come out of that center conductor, they were referenced to the shield from the inside. Now the fields are coupling between those 2 wires going up between the ends of the wire, and that is extremely little capacitance. And that is field mostly between the 2 wires. How does it get down to the ground? And that line going down and curving is like 20 feet, 17 feet on a 20-meter dipole. Moving the bottom of the line near the ground doesn't do anything. Moving the top does, and that shows there's coupling between that wire on the left at the circle and the dipole wire taking off to the left. There's field coupling between that and the shield. And this takes us to this idea of this nonsense of putting ferrite clamps to stop current from going down the outside of the shield. Firstly, there's no such thing as outside of the shield. It's little round wires, they're conductors. There's no inside, there's no outside. Inside and outside are only mechanical. And with regard to the fields, not the current. the charges between the center conductor and the shield for the fields inside the wire coupled between the inner surface of the shield and the outer surface of the center wire. That's just for the charges. Current doesn't care. Current will go all the way around the wire if it travels. What this shows is that the coupling to eventually end up over here coupling with the ground begins right here. It begins as that wire comes out and starts going this way. There's field coupling between here and here, like such, between the wire and the outside of the cable. In other words, the wire and the charges on the outside of the cable, the shield. The lines of force don't couple into the coax, and they don't couple to the other side of the shield on the inside. They couple to the nearest surface. As that distance increases, as charges go further out to the left along the wire, those lines of force get weaker and weaker because it's very quickly traveling away from the shield. And at some point, they'll jump off and connect to the ground. Because under Gauss' law, I think it is, the magnitude of the force lines is proportional to the square of the charge, or the charge on each conductor times the other, and the square of the radius, and that's modified by cosine theta. So as distance and angle increases, those lines between the wire and the shield get very weak. But that's just what they need to jump off and couple with the ground. And that there is the secret of what causes the dipole matching. So this experiment here was with the handy-dandy capacitance meter on a support here with this transmission line out horizontally. That's a dipole, just hanging, 9-degree orientation. And I took a wet sponge because water has a very high dielectric constant. I measured 139 picofarad across the wire wrap wires. The wire wrap wires have essentially no capacitance between themselves. Kiner has a low dielectric constant, and the wires are extremely small. But when I brought the sponge between the outside of the coax and the bottom wire soldered to the braid, nothing happened. When I brought the wet sponge very close to the plastic jacket on the coax and the upper wire, the capacitance started increasing. That's obvious. It was something like 2 picofarad. And of course, get the wet sponge close enough to the top wire to touch it, then it all jumps and goes crazy. But that's not reality. The point of this was to get a feel for how far along that coax that effect occurs. And in this very limited test, and a very crude test, it was about 2 inches. The wet sponge, which is a huge, water's a dielectric constant of 8.4, I think it is, it increased a couple picofarad on the meter. That isn't much, but it's a tremendous amount more than 0.03 picofarad between the ends of those two number 6 wires. So there are essentially 2 coupling mechanisms to get out of the line and out to the wires down to the ground. Between the lead wires from the coax to the antenna wires, then the antenna wires, and believe it or not, both can couple back to the shield, even the ground braid connected to its wire. Because realize as distance moves, the wave timing is different. The 2 coupling mechanisms, the lead wires coming up to the ends of the antenna wires, between the antenna wires, total capacitance there may be a half a tenth of picofarad, but several picofarad between the wires and the shield. And that's the coupling mechanism that results in the sensitivity of a dipole with regard to the length of the transmission line. The length of the transmission line towards ground doesn't matter because the coupling is not from the wires all the way down the coax to the ground. partway down, the lines of force will jump off and couple with the earth. And you can test that by holding the transmission line still at the feed point and start bending the line towards the center conductor side of the center conductor arm of the dipole. As you go further and further up and bending it, you'll start to find a point where it'll change SWR. And that will show the extent of the fields. And that'll change with power levels, because power levels change the potential, the voltage levels, and that changes the field coupling. When I tested the 20 meter dipole at very low powers, I was expecting coupling between the feed point and a nearby tree. I didn't get it until the powers raised considerably. Then it jumped off with field lines over towards a tree. So there's the answer to the mystery that's been bugging me day and night for months. And you might be able to hear a little Cheech and Chong in the background. Cheech and Chong's Get Out of My Room. So anyway, this is what amateur radio is about. Not pushing buttons on that. So update on the unfed, absolutely deaf as a post. I connected the Kenwood 430 to the 80 meter dipole, 130 feet long. Picked up pretty good up to S5 signals on 15 meters. When I connected the 15 meter dipole to the Yaesu, and I've compared the S meters on both, they're about the same. I got weak S readings and readable signal. When I connected the NFED to it, I got squat, nothing. So NFED, very poor. Now, if that NFED wire were as long as a dipole wire, that might be different, because antennas don't work the same in receive as they do in transmit. But the question there is something called aperture, and how much of the incoming field the antenna is parallel to, and how much that field excites energy into the wires. And obviously, the shorter the wire, the less receive energy. That's not necessarily the case on transmit, because with the unfed, pardon the cough, sciences in East Tennessee, the unfed had no problem reaching Dominican Republic and Puerto Rico and Utah on the CW RBN spotter. So reciprocity is a question. There's reciprocity between transmitting and receive stations at a distance. There's reciprocity, or lack of it, between receive and transmit on the antenna. And the NFED was absolutely worse than useless on receive. So N1SCA is right. NFEDs suck. Give it up. Go home. Build a dipole. 2 wires. KBOIP did it.